This PhysCast is going to look at using the Heisenber Uncertainty Principle in the example of an electron in an atom. Pause the video and read through the question carefully. Now that you've read through the question, you can see that we're considering an electron that is constrained to a region of space, and that constraint in position should give us some understanding of maybe a limit to the momentum value that may also then give us a limit to how small the energy of this system could be. So let's start with a quick diagram here. We're saying we've got basically an atom that is defining some region of space in which our electron must be found. That's what we mean by having an electron kind of attached to an atom. So our electron's in here somewhere. We're not quite sure what it's doing, but we know that if it's going to be forming a hydrogen atom with the nucleus in the center there, then it never gets much further away than about an angstrom. That's in the ground state. So we're saying here basically this region of space for our electron is somehow roughly an angstrom in size. And you might have to recall that an angstrom, not an SI unit there, is 10 to the minus 10 of a meter. So a tenth of a nanometer. So we could say here that we know the uncertainty in the position of our electron here is something on the order of 10 to the minus 10 meters. And that tells us immediately from the Heisenber Uncertainty Principle, using the product of the position and the momentum uncertainties here, must be at least h bar divided by 2. So if we've got a fairly small value here for delta x, that tells us straight away we're going to have a limit as to how small p could be, because delta p here is going to have a limit. Obviously here the uncertainty in momentum here must be larger than h bar divided by twice the uncertainty in position. Now this problem is a little bit more complicated than we're doing here. This is actually a three-dimensional problem, and of course this here is really just the one-dimensional version. There would be an uncertainty in the y direction, there would be an uncertainty in the z direction. So we're not going to get an exact value out of this. Similarly, this determination here of our uncertainty in position is not really exact. It's kind of an order of magnitude approximation. We haven't calculated an exact value for the uncertainty in the position here. We're just kind of knowing it's roughly on the size of 1 angstrom. So we're only going to get out of this a bit of a order of magnitude as to what this uncertainty in momentum tells us about the smallest value momentum could be. So if our uncertainty must be larger than this, it tells us that our actual momentum of the electron here must be sort of on the order of h bar on 2 times delta x. Now the question didn't really ask us about the order of magnitude of the electron momentum, it asked us about the energy. So for the time being we'll assume we can use a non-relativistic form of relationship between momentum and energy, and we'll say this is basically p squared over 2m. So that our energy is something like that, which in our case here means will be something like h bar over twice the uncertainty in position squared times 1 over 2 times the mass. So now we can put some numbers into this expression here. Planck's constant we could write as 1.05 times 10 to the minus 34. That's not Planck's constant, sorry, that's Planck's constant divided by 2 pi. That is h bar, that's in units of joule seconds, divided by twice our uncertainty in position, which we're saying here is something like an angstrom, 10 to the minus 10 of a meter, and that's being squared. And then we're going to multiply that by 1 divided by twice the electron mass, which, write that down here as 9.1 by 10 to the minus 31. And you do that calculation and you get a number out here that's something like 1.5 times 10 to the minus 19 joules. Okay, quite a small number. And in fact, a better way to think about that, if we divide by the electron charge magnitude there, we'll get something that's, well, let's keep our approximations. I'm not going to do an exact calculation here. I'm going to say this is something around 1 electron volt. So we're saying the energy scale for this electron that's constrained to basic atomic dimension here is going to be around an electron volt. And in fact, if you've done any work at all with atomic energies, you know that 1 to 10 kind of electron volts is a reasonable figure to have there for an atomic energy, particularly close to a ground state. So that seems to have given us a pretty good feel for exactly what kind of energy scale we're dealing with here, simply based upon the uncertainty principle. One other check we could quickly do here, which is interesting, is to go back and look at this expression that we have just here. and say what would happen if instead of an electron kind of constrained within an atom, we thought about a nucleon contained within a nucleus, so a proton or a neutron stuck inside a nucleus. And there's a couple of things we should be able to see here about whether we expect this number to stay the same or be much larger or much smaller than for an electron in an atom. The first thing is this mass term out here. We're dividing by mass, so we certainly expect a smaller energy here because the mass of our proton or neutron is going to be much larger, like almost 2,000 times larger. So basically we should expect there maybe something like 3 orders of magnitude smaller. But then there's this constraint in here, this uncertainty in position. And to be inside a nucleus is a much, much tighter constraint. It's something down, rather than being on the angstrom level, 10 to the minus 10, it's kind of down on the femtometer scale, down at the 10 to the minus 15 meters. So there's 5 orders of magnitude smaller. In fact, this thing is being squared. There's something like 10 orders of magnitude smaller on the bottom line, which of course gives us 10 orders of magnitude larger, which certainly overwhelms this mass effect here. So we might expect to have much, much larger energies involved with nucleons inside a nucleus. And indeed that's the case. These are typically hundreds of thousands to millions of times more energy involved for nucleons stuck inside a nucleus than for electrons inside an atom. So this kind of tells us this approach here actually does seem to be consistent with the energy scales that we see for these kind of microscopic systems.